All right, here we go. So today we are going to talk about multiple problems. On the top I have written solubility, equilibrium, free energy thermodynamics, electrochemistry, gases, liquids, and solids, and then we'll practice a little bit of chemical equations if we have time. All right, so I'm just starting on the front, just moving right around. Again, we'll go in and out a little bit. We'll go through some problems together. We'll do some of it on our own, come back, see where we're at. If you need a calculator or anything else, I have a couple extras, but we should probably have one eventually. We'll need for a few. All right, so away we go. First one, this one is from 2010. Several reactions are carried out using AgBr, a cream-colored silver salt, for which the value of the solubility constant, product constant is 5.0 times 10 to the negative 13 at 298. So A. Write the expression for the solubility product constant KSP of AgBr. I'm going to give you a chance to write that. Can you get that point? What would that look like? They don't give you a formula or anything else. What would that be? And if you don't know, after today, hopefully that will be a little more cemented. We've done a couple of KSPs now lately, so not far away. As you're finishing that up, if you're stuck, you've got to remember this. This wasn't given to you. That whenever we're talking about KSP or a solid, it breaks up into its ions. Okay? Always breaks up into its ions. There is no other perception of this. It's not like, well, how do you know it's on the left or the right? It's a solid. Will it break up? If the K is large enough, it goes to the right, and then we consider that soluble. Okay? If it's not, it'll stay as a solid. So, that being said, hopefully you wrote something to this effect. And that's it. There's nothing else. KSPs will usually, I can't even think of one, will always have products only, so it's much more simplistic than most. 1 point is earned for the correct expression. Ion charges must be present, parentheses instead of square brackets, not accepted. Got to have brackets. Why? Because brackets are concentrations. Okay. All right, moving forward. B, calculate the value of Ag plus in 50 mils of a saturated solution of AgBr. Okay, so I'm like, well, I'm not sure what to do here. If you had written this all out, and this is why I actually wrote this out here initially, is that this is just me thinking. This would be in the beginning zeros, so you have plus x. Like this isn't for this problem. This isn't unique. This is how KSP problems work. You start with nothing dissolved. So if you have, let's just say 2 BRs, then you'd have 2x. If you have 2 AGs, you have 2x. Here you just have a 1 to 1, so it's XX. So what I can think about is if I'm asking what is the concentration of Ag plus, all I have right now is a KSP. So I have to utilize this. So at equilibrium, meaning at a KSP, and this is the one thing, it just doesn't seem to seep in as easily as the rest of equilibrium questions. At equilibrium, the amounts reflect the KSP. The KSP helps reflect the maximum amount that can dissolve. So if I have this as my KSP, what is that currently equaling? X squared, right? X times X. So what you need to just do is solve for what 1x would be. So this is truly x squared, so you take the square root of your KSP, and you should have x, which equals both. But it's asking just for the concentration of Ag+. It says in 50 mils. Doesn't matter. We're already in concentration. It's not asking the amount of moles. Moles are different. Then there's an actual amount. Concentration's concentration. It's already a ratio. It's just telling you there's a certain volume. So when you're all said and done, I hope you are doing this. You're just waiting for me to calculate it every time. got something around that line. It's always good to just bring up. They're establishing the only sig figs that they're throwing in here right now. There's 2, so it's 2. If you're doing 3, you're still really safe. It's kind of what I keep saying. It's plus or minus 1 usually I've seen. I can't think of any other situation that hasn't come up like that. So if you stay at 3, usually they do 2, 3, or 4. Okay, moving forward. C. All right, bigger part here. A 50 ml sample of distilled water is added to the solution described in part B, which is in a beaker with some solid AgBr at the bottom. The solution is stirred and equilibrium is reestablished. Some solid AgBr remains in the beaker. Is the value of Ag plus concentration greater than, less than, or equal to the value you calculated in part B? Okay, let's talk about this. When I'm confused, I draw. I'm very visual. I like to think about this. So let me just restate this once, because I think a lot of people would have a hard time with this. There was a solution of that. Okay? Then what I did is I added basically some water, extra water, onto this. It says some solid AgBr remains at the bottom. Maybe this drawing won't help you, maybe this one will. Is the value of Ag plus greater than, less than, or equal to the value you calculate in part B? Now first, let me just ask, adding water, it was saturated before. Adding water to a solution and then all of a sudden solid showing up, does that make sense? Like let's say that I didn't have any solid, because it didn't say I did before. By adding water, would it make it so it's that solution can hold less or more usually? Just I want to talk about that first, in theory. It should be able to hold more, right? So there shouldn't be any solid on the bottom. But there is, and there's a reason why there is. I just want to say that. So wait, you're like, wait, what are you talking about? If a solution can only hold so much, let's say it's at a maximum, it's saturated, and then you add more water, it should be able to hold more. So there's a reason why they have this here. They're saying that they dumped in a bunch of this, and there's still some on the bottom. And then they restirred it, and equilibrium was reestablished, meaning that this is now, and this is the key point, because equilibrium what does that mean? That means that I am maxed out. I am saturated. These two are saturated. And how do I know that? It's because I know that there as much maximum has dissolved, so solid remains. So anybody have any thoughts of basically the concentration of the saturated solution of AgB or Ag? Of Ag. How does that compare? There was a saturated solution. This is saturated. And now I add some water, but they're still solid on the bottom, but they're basically saying equilibrium was reestablished. Yeah, exactly. And maybe I'm making that confusing, but I'm trying to establish something. If I didn't have the solid here, the concentration I would have to say is less. Why? Because I'm assuming it started with a certain amount, that, let's say, and then I added water. Well, it's a ratio. The volume went up, so moles over liters. The liters cause that to go down. The concentration will be less. Kool-Aid, you put a lot of water in it, doesn't taste good, concentration's down. Kool-Aid. But because they're solid here, you maximize the amount that dissolved, and whatever was left can't. So it's the exact same amount, because KSP, equilibrium, is always the maximum amount. So it should remain the same. I don't know if that, if you have any questions, then ask, please. Like if you're like, wait, I don't remember. If they didn't put the solid there, we don't know if more could dissolve. That's the whole point why they put that solid on the bottom for you. Oh, wait, there's a solid on the bottom. I don't get it. Because the max, they stirred it. All of what could dissolve did, and all that didn't did not. Is there more moles in this one? Yeah. There are more moles in this one because it's a larger volume, but it's the same ratio, so that's what molarity is.
So the value calculated in part B was like the max.
Right, so the concentration of Ag plus is that, and of 7.1 times 10 to the negative 7, and in the second situation, it's also 7.1 times 10 to the negative 7 molar. Yes. Are there more moles again? Yes, because there's more volume. It's a ratio. Okay. So, but as I always keep saying, keep it in perspective. That's worth 1 point. So if you didn't get it, you didn't get it. You move on, and it's probably not contingent on the next one. So just kind of keep that in mind. All right, D. Calculate the minimum volume of distilled water in liters necessary to completely dissolve 5-gram sample of AgBr at 298 K. So why do they keep saying 298 K? Is because that's the condition that we're under. Okay, the minimum amount of volume, meaning that it will be saturated. So, how do we do that? Well, what are we trying to, what do we know about equilibrium or the molarity or anything else or the volumes? Well, we know that 7.1 times 10 to the negative 7 molar is the maximum amount that can dissolve. So what they want to know is, I'll reread it, calculate the minimum volume in liters necessary to completely dissolve 5 grams. So I would make it saturated. Right? I mean, it would be completely full. So I need moles over liters. Still need moles over liters, comparing it to my molarity. It gave me grams. Whenever I'm talking about volumes, molarities, things like that, you got to think probably that the grams will go to moles. Grams usually always go to moles. They helped you out a lot. Really nice. They give you a molar mass. Do not ignore it. I mean, they're giving you the molar mass. They're not saying these kids can't do molar masses. Like, they're basically saying use the molar mass. If they ever give you molar mass and you have a mass already, my gosh, that is definitely something going on. So, what I'd like you to do, if you don't know how to write it, think about what needs to happen. I'll give you about a minute. What would have to happen here? I want to know the minimum volume. So think about it. You have moles. You have something else. I want the volume that would dissolve this, but the minimum. Why are they asking that? Because I could just say, well, give me the ocean, and I will dissolve this. Or give me the Atlantic. I won't even be greedy. I won't take the Pacific. I'll take the Indian. I'll take the third largest, and I'll throw 5 grams in it, and it will dissolve. Now, what's the minimum amount? By the way, this is an insoluble compound, meaning that it's not very high in solubility, but everything dissolves if you have enough water. If you have enough. Someone elaborate. Oh, choked up about this every time. Someone elaborate what you think for what you're doing with this. Luke?
I divided it by, I took 0.0266 moles and then did a T-chart for 1 liter over 7.1 times 10 to the negative 7 moles.
So you're like solving for a new molarity, like you're using molarity with the relationship to moles and volume. Yeah. Yep, perfect. And mine's gonna look different, and what you did is perfectly fine. I'm gonna set it into, it's good. I'm gonna set it just into the molarity, like moles over liters equals molarity. And that's what you did as well. So it's good to hear and see different things. So if you're like, I started doing a T-chart and I was canceling things out, great. I like to plug it into the actual calculation. Like this is, right, this is moles over liters. One way is not right. Good to see and hear different ways. And then it just asks, again, liters. It asks the volume. So this should be really big. If you're like, wait, why is it so big? KSP problems are about quite insoluble salts. Like they're very insoluble. We're not talking about things that dissolve really easily. We're talking about things that barely dissolve at all. So when it's all said and done, the answer is in scientific notation, but you can definitely not have it in scientific notation. That would be the answer. So if you got that, that's awesome. 1 point is earned for the calculation of the moles. You should have figured out that you probably should have done moles, right? They gave you a molar mass. They're pushing you that way. And then 1 point earned for the correct volume. So that's a lot. I mean, that's a lot of liters. All right. I hope that makes some sense. Again, please ask. Wondering where things go. Again, the question wouldn't be the maximum amount, because you could just go unlimited. It's the minimum amount that you would need to dissolve all that. KSP helps us. KSP got us to that. That's the saturation point.
So did you say they gave you a point for finding the moles?
Yeah.
What if you just continued that T-chart and went right into?
Then you would get it, because good question. Yeah, like sometimes we all kind of go further and we do like all of it at once. Within that relationship, you've done that, so yes, you get the point. So before I leave, I just want to say one more time: the KSP earlier found us this value, the 7.1 times 10⁻⁷. What that means is that's the maximum molarity, regardless of volume, that can be reached of AGBR. Can't get any more concentrated than that. And that's been determined by other people for us already. Okay. E. A student mixes 10 mils of a 1.5 times 10⁻⁴ molar silver nitrate and 2 mil 5 times 10⁻⁴ molar sodium bromide and stirs the resulting mixture. What will the student observe? Justify your answer with calculations. What are you ultimately just saying? What do you mean, what are they going to observe? Because you got to kind of understand what the heck they're looking for. Will a precipitate form? Okay, so if you're reading it like, oh, yeah, I didn't read it like that. Got to understand, when we're doing KSPs, what will be observed? It's also, guys, a double replacement reaction, right? I mean, so that's the only evidence of, let me just write that down. It's the only evidence of a double replacement reaction is if a precipitate forms, or maybe a gas. That could definitely be something. But you have this, and you have that, right? So voila, this is it, right here, the AGBR. It's making AGBR. Will AGBR be made? Now that's not a net ionic. A net ionic would just be Ag plus Br minus, gives you AgBr. So, how do I do that? The only thing that I have to help me is the KSP expression. This, right? So, specifically right here. So, these are values. They gave me values already. Are these at equilibrium? I don't know. So what I have to do is I plug them in. I have to plug them in C. So what am I actually solving for initially? What's the phrase? What am I solving for? I'm not solving for KSP. I'm solving for Q. To see if it precipitates. Okay? Let's take a look. So, here's the thing. It doesn't hint this to you, but you have to get this right. The volumes add. So I'm going to do this all at once. Here we go. The Ag plus, if you don't like it this way, that's fine. You can definitely do it another way, but this was the molarity of the AgNO3. If I take this and multiply it, what unit am I in? Hunter, what unit am I in right now? Yeah, not many.
Millimoles?
Yeah, there you go. And then if I just divide it over the total, I'm back in molarity, right? So that's the molarity of my Ag plus. So please finish this up. Do the Br. And then what I'd like you to do is plug that, well, we're plugging that in. What's the relationship of Q to K? Meaning greater than, less than, or equal to. And then say it. What does that mean? To me, on this so far, that's probably the hardest problem on here. It's hard for you to recognize that that's what you're supposed to do. It's not always so familiar. Can you want a different calculator, or are you okay? Okay.
Do an extra little sheet.
Yeah, it was on
Oh.
I'll tell you now, the answer key does not do it the way I'm doing it. They like to do it separately. But at some point, putting it all together just sometimes just makes more sense. If you want to get each value separate and write them in, that's absolutely fantastic.
Can we use liters instead of
Definitely, you can use liters. Only reason why I don't like to use liters is that they're both in milliliters, so they cancel themselves out. But you could definitely use liters, but then you got to use both in liters. So to me, it's a waste of time, and I have such a fear of extra conversions of causing there just to be a random error, because that's what happened to me all the time when I was a student. Phone's blowing up. You plug that in. Should have gotten something around this, I hope. So what does that mean? Larger or smaller? Greater than or less than Q to K? Q is greater, isn't it? What's the other? Is it negative? Because K is negative 13? So what does that mean? Yes or no to precipitate? Yes? I always imagine the K in the middle. So what does that mean? Q's to the right. Q's over here, right? Here's Q in my mind. So Q's got to drive back to K. So it's driving back this way. Yes, precipitate will form. I have too much. And to be honest, just the fact of the previous problem, not that you can just say, well, previously, if you need that many liters, of course it'll precipitate. Can't say that, but I mean, you need so much liquid for this to stay in solution, and you don't have that right now. We're talking about 12 milliliters. Just saying. So, yeah, a precipitate will form. So, if you're wondering, how do I justify it? By doing the work, by saying that is larger, you don't need to explain more than saying the precipitate will form. You don't have to start saying where the Q is versus the K and all that. I need you to stay away from trying to feel like you need to explain it more. But you do have to say enough. So that's also what this whole couple weeks are for. So a precipitate. Okay. Finishing up. And then this is one of the longer ones for today. Thought I'd start off right away. F. Last two. A color of another salt. And you got to really slow down. Sometimes this gets a little confusing of what's been given to you and trying to keep track of it all. A color of another salt of silver, AgI, is yellow. A student adds a solution of NaI to a test tube containing a small amount of cream-colored AgBr. After stirring the contents of the test tube, the student observes that the solid in the test tube changes color from cream to yellow. I. We'll talk about that in a second. I. Write the chemical equation for the reaction that occurs in the test tube. Well, maybe we should talk about it now. So you had AgBr and you add NaI to it. Okay? So it was cream, it turns to yellow, and it asks to write the chemical equation. It does not say net ionic. Big deal. So write it out. If you don't, try it. It tells you the product. It tells you something's yellow, and then it says it became yellow. Just saying. Again, there's two ways you could write this. It doesn't have to mean anionic, though. Doesn't ask for states or anything. I'll even give you a start if you're like, I have no idea. Because they're right there. Wow. I hope we're not waiting for me on this one. Right, there's nothing else to do. If it were net ionic, by the way, just so you know. Whoops. Yeah, this would be this way, and then this one would be like that. NAs would be canceled. That would stay in solution. 'Cause that was a solid in the beginning. Now that's a solid in the beginning. If you do that happen. Double I. All right, this is where we have to think about this. Which salt has a greater value KSP, AGBR or AGI? So which one has a greater KSP? What does that mean? It means that one dissolves easier or faster or has a higher solubility, however you want to view it. So based on the evidence, what we basically just did is you started with AGBR, and it's asking between AGBR versus AGI. Started with AGBR, you put in NAI, and this was cream, and now it turned all yellow. And it says that yellow is AGI. So which one is more soluble? Which one has a greater KSP, AGBR or AGI? AGBR? It was a solid. I poured NAI in, and what happened? The AGBR dissolved, and the AGI stayed as a solid then. It turned into the solid. So AGI is much less soluble than AGBR. So this would have the greater KSP. I'm going to read exactly what it says. It says AGBR has a greater value KSP. The precipitate will consist of less soluble salt. When both I minus and Br minus are present, because the color of the precipitate in the test tube turns yellow, it must be AGI that precipitates. Therefore, the KSP for AGBR must be greater than the KSP for AGI because the AGBR dissolved. Or the BR at least. The AG had to stay because it clombed on the I.
Can you explain that one more time, please?
Yeah. So basically, I mean, do the best I can with this. Cream. There's some cream. Isn't that obvious? There you go. I'll outline it. There. So there's some in there. Morning. So I put NAI in there. And because of that, the reaction between them produced AGI. And you're like, well, wait, why couldn't it have produced AGBR? It can only do it if it is soluble, if it can actually go in the solution. So what happens is the BR, maybe the actual net ionic is better to show. This reaction, and you're like, well, how'd you know? They told me it happened, so I'm moving forward. It happened. The BR dissolved, and the I went out of solution as a solid. So as a result, what it's proving is that this was a solid, and now this is a solid. This one actually went back into solution, but this one couldn't stay in solution. It became a precipitate. So whatever one was standing, basically here it is. If you have two solutions and one dissolves and one doesn't, the one that's sitting as a solid is the least soluble because it's not dissolved. So that would mean that it would have a much lower KSP. And if you ever get confused by amounts, always keep in mind the equation. The larger a K, the more we go this way. So the smaller it is, the more we're going to be that way. So that would make sense that if I become a solid, I would have a smaller KSP than something that isn't a solid at the time. Okay? So it can be confusing. I totally get it. KSPs are. They're just different. So that's the end of that problem. But you want to guess how much that was worth? That was worth 1 point. What did you say? 13. Even though nothing's worth ever more than 10. All right. Flip the page. We are going to the next one. All right. So, little thermodynamics, a little free energy for you. So I put the table up here. These we should be good at. So KSP, I always feel like people have a little bit of uncertainty with it. But this one, I'm hoping, I'm going to let you kind of talk about it. So please kind of talk with each other before or with yourself. If you like to talk to yourself, that's fine. I can understand. It says, answer the following questions using the information related to the reactions X, Y, and Z in the table above. A, For reaction X, write the expression for the equilibrium constant Kp. So please, for reaction X, please write the Kp now. Grape juice is gone. And when I was a kid, my parents could never buy grape juice because if they ever did, I would just take it and then like run somewhere and just slam the entire thing every time. And now I haven't had it for a long time, and I'm just like, oh. Like I'm hearing voices right now. It's like I need to go buy more at Costco or something, you know, like the big tubs or something like that. All right, I hope that's what you wrote. If you wrote any more or any less, it's not right. If you wrote brackets, it's not right. You cannot include the water, or the carbon, sorry, because that is a solid, right?
You put parentheses around stuff.
Are you saying like this? That's okay.
Okay.
But don't put brackets around your pressures.
Okay.
Okay, yeah, that would be okay.
Oh.
So you found that loophole. Yes, you could put parentheses, but that's it. 1 point is earned for the correct expression, but it has to be like that. So please, make sure that you are writing them correctly. KPs. KPs have to deal with gases only. They won't be an AQ in a KP question.
Would they want you to write like the KP of X? Like,
Oh, no, no, I don't think so. Yeah, I don't know how you do that. I mean, you have to literally almost write of X. You're doing it of X. You're answering it. So. B, for reaction X. Hey, we're staying at X. Well, the equilibrium constant Kp increase, decrease, or remain the same if the temperature rises above 298. So, first, I don't see. Okay, here's a great question. Okay, it doesn't say this yet, but all the little degree signs in the actual table, this means that standard conditions, right? But they also are telling you the actual literal temperature. So right now, just so you know, all these reactions, the data is coming from 298 because it actually is listed right there. So just understand situations. It also means at 1 atm. So will the Kp, will it increase or decrease or remain the same for X if I increase the temperature? So here's my question. What are you looking at? I don't want an answer of what increase, decrease, remain the same, but what do you have to look at? What gets you to the answer? Enthalpy is about heat flow. It's all about the enthalpy. Okay? You can't just be like, oh, it increases, it automatically goes to the right or left. It doesn't automatically go to the right or left. So this means that it is endothermic, and that's what I'm going to use, but mentally I'm going to place that E. I'm going to place that E where? Left or right? It goes on this side, because it's a nice visual then. So with Le Chatelier's principle, whatever you, it always shifts away from the addition, right, towards the subtraction. So the reaction is going to shift to the right, which causes what? K2 increase or decrease? Increase. How do I know that? Because you're going to make, let's get rid of these Hunter parentheses here. You'll drive it to the right, so you're making more of this, right, and less of that. So you're making more product, less reactant. So my explanation would be, by raising the temperature, it will cause K to increase because it is an endothermic reaction, which causes more products to be made. Right? Just state what's happening. It's endothermic, drives to the right, more products will be made. Okay? So AP definitely increases though. All right. 1 point. C. And these are shorter, but they're all really important. For reaction Y, hey, we're moving on. At 298, is the value Kp greater than, less than, or equal to 1? Justify your answer. Oh. What? Huh? Okay. This is a long time ago. I don't think I've actually restated this for a long time. Let me say it one more time. Will it be greater than 1, less than 1, or equal to 1? What does it mean when K, is it just KP still? I don't want to mess this up. Yep. What does that mean? What? But what does that mean? Brody, hey Brody, everyone. Equal reactants and products. So I'm like literally like equal on each side, right? So that means the reaction isn't favoring either side, right? So what tells me of H, S, or G which way a reaction actually goes? By just understanding what each one does for me, I can answer almost any question here. But that's the foundation. So if you focus on the little questions, it's never going to help you. You got to know what they do. So we're going to get this one out of the way right now. That's not going to help us enough. When you have all three, there's only one that will help in each situation, usually. So this is about energy or heat flow. So when we're talking about changing temperatures, great. I go right to enthalpy. Entropy does what for me? Disorder. So if I'm gaining or losing order, I talk about that. Free energy does what for me? If it's spontaneous, what does that mean? It means if it naturally will move forward without any intervention. Like, so it'll naturally go to the right. So, what does this tell me? What, Brody? It's not spontaneous. So what does that mean? Which side is more favored according to change in G? Remember, G has to be negative for it to be spontaneous. So, will Kp be greater than, less than, or equal to 1? It should be less than 1. Why? Because it's products over reactants. I have it right here. I'll make more of this and less of that. I know it's not the same equation. Right? So Kp will be less than 1 because change in G is positive. Favors reactants.
So if changing Z was 0, would that mean Kp equals 1?
Yes. And question was, if change in G was 0, would Kp be equal to 1? Yes. Because we're not going anywhere.
Is that the only time?
Yes. I hope these are making, like, this is the root of what we need to know each time. And what I like is that these are usually pretty consistent from one to the next. So the more you just understand what they all do, you got to know the signs. Right? You got to know what it means. Those kinds of things, if you have that down, you can answer almost any question based on that. Erica. So that would have been, in this case, is if this was negative, so that meant that the overall reaction would be favoring the right. So then Kp would be greater than 1. And that's weird too. It's like, wait, so all it has to do is have a negative side and it means it's going to the right? Yeah, because that means it's favored to go towards the right side. D, for the reaction Y at 298, which is larger, the total bond energy of the reactants or the total bond energy of the products? Okay, so this one, I have a feeling is going to be a very good one to talk about. All right, so let me review what I'm doing. For reaction Y, which is larger, the total bond energy of the reactants or the total bond energy of the products? First, if you're not sure what you're looking at, I think we do need to talk about this. So we're doing reaction Y, bond energy. Anybody remember when we break or make bonds, what variable we had? And we did it really early. Like, see, when I was a student, I always tried to envision where I was sitting and everything else and when it was. We did this in like chapter 8. So which is the only one we learned about at that point? H, right? Didn't we just learn about S's and G's? So if it's like, wait, bond energy. I know I did bond energy a while ago. Then it can't be S and G. I don't know if that those kinds of things should help. Like when you're sitting back and you're envisioning where it was and what happened, like we've been doing that a while. Those aren't all together. So, what does that mean? It means overall I've gained energy, right? From the beginning to the end. So I've gained energy. Let's talk about, that's the first part. Let me just make sure I'm answering the question. Okay, bond energy, the reactants. Okay. I'm going to write it down formally down here. What has to happen from here to here? Bond energy. Meaning, yeah.
You have to put energy into the system to make it separate.
So we need to break these bonds, right? So we have to break these, and we have to make these or form, right? That's how it always has to happen. You have to break them before you can make them. That's what my tattoo says. So, is the total bond energy of the reactants or the products greater? If it's an overall positive, which one would be greater? And it's in this order. Which one would have to be greater? You have to put more energy into breaking them, and then not as much energy was released forming them because I retained some. I have leftover energy, basically, is what it's saying, right? I mean, you only get energy from breaking them first. So you got to put money in first, and then it's like you took a withdrawal and you still have some left. So the answer should be, if I'm phrasing it correctly, it's the bond energy of the reactants. Because, you could say, because it's endothermic, or because the overall energy is plus 41. But if you want to talk about making or breaking, I will read exactly what it says right now. It says the total bond energy of the reactants is larger. Reaction-wise, endothermic, plus 41 kilojoules. So there's a net input of energy as the reaction occurs. Thus, the total energy required to break the bonds in the reactants must be greater than the total energy released when the bonds are formed in the products. In this case, that's, I mean, you'd write more than that. You'd write, it just needs to be one power sentence. It doesn't need to be crazy. But the reactants is larger. It's the reactants for sure. All right. Almost done. Oh, whoops. There's still another part. E. Is the following statement true or false? I don't like these. I mean, I like them, but I don't like them for you. They usually try to trick you. So don't just all of a sudden go, oh, yeah, I know. Slow down. Usually it's the, don't do this either, but usually it's the exact opposite of what you think first, but don't automatically go, oh, I thought it was true, so it must be false. You need to slow down on that. But here we go. Is the following statement true or false? Justify your answer. On the basis of the data table, or the data in the table, it can be predicted that reaction Y will occur more rapidly than the reaction X will occur. Again, I will say this one more time. Is it true or false? On the basis of the table, the data in the table, it can be predicted that reaction Y will occur more rapidly than reaction X. I don't know. Anybody?
True, because the change in G for reaction Y is smaller than the change in G for reaction X.
But in a funny way, they're both non-spontaneous. So I hear what you're saying. So you're saying, like, if one was going to move forward more, the reaction Y would, because it's less positive.
Yeah.
Okay.
Hold on. Okay, I got X, and that would be false, because in X, the G is more positive, so it's making more reactants.
Okay. So you're saying because it's two-way arrow, like this is actually going to be rapid, it's going to go that way.
Yeah.
Spontaneous. You want to go, Hunter?
I was just gonna say it's false. I was gonna say false because one has C, not CO2. They're different reactions.
Okay.
2 hours.
Spontaneous is not about like, oh, they're so spontaneous, so they do things so quickly. If a boulder rolls down a mountain and it takes 1,000 years, but nothing ever intervened and it just did it by itself, That was spontaneous. So, this has nothing to do with speed. What is the chapter we talked about with rates and speeds? It ended in kinetics.
Kinetics.
Gosh, Leonard, you are so good. It's false. Here's the key word in the statement. Based on the data in the table. Based on the data in the table, we don't have enough information. It's only based on kinetics. We don't have a rate. If you're like, oh, they aren't going to do that again. They will always do that. It's about understanding things. Speed is only based on kinetics, on rates. You need time. There isn't one thing about here that talks about time. Right? Luke?
So like for the rock example, if the
That would be a negative G for the
yeah,
rock.
if it was like more negative, let's just say for like a reaction, what does that mean? That it's just more likely to continue to be spontaneous, or does it not? Are they the same if they're negative?
It will drive it more to the right. You'll make more of it. But I know that's hard. It's like, what? Then that would go fast. It's not about speed. It's not about speed because there's other things to take into account: collisions, how they collide, the temp. Well, there is temperature there. Other environmental issues that would be considered.
If one G
Rate or order. Sorry.
One G is negative and one G is positive, does that also, or does that change?
That good question. And I think that would actually even been a better form. Like if you would have made y a negative and x a positive, it still wouldn't have mattered. But that would have actually been a better trick because it's not about. There's no time here. It goes which one will occur more rapidly. Okay, it's not about speed. You have to know order and everything else. So we don't have that. So if it ever talks about speed, it's only about kinetics. Is what I'm trying to just get across. Okay? And I get it. There's could be so many questions. What about this? What about that? They're going to keep it about at this level here. Just hey, they gave it to me or they didn't. They gave me rates or they didn't give me rates.
So how would you word that? Like false because
I would say, well, I'll read what they have, but then I've kind of been saying it. But thermodynamic data for an overall reaction have no bearing on how slowly or rapidly the reaction occurs. I just wrote kinetics only as well. Like I wrote there's no indication of time, which would have to deal with kinetics, which has not been given. You have to say true or false, and then you have to say why. So I would just say something like no time or rates have been given or provided.
What if you said because there's not enough input?
I feel like you'd have to say what info you need, or even just say there's no mention on time. I think you'd have to say something. You could maybe get away with it.
so you would say false right there?
Yeah.
It's false.
Yep.
Could still be true. You know what I
No,
mean?
it's false.
No.
It can't be true. It's false because there's not any mention of time.
But like if there was mention.
But there isn't.
Oh, based on the table.
Based on the table.
Okay.
Because you're saying in like Africa, this would happen.
So if a leprechaun is doing this. F, consider reaction Z. Oh my gosh, we're getting to it finally. It's like you've been waiting all the exam. Is change in S positive, negative, or zero? So what is change in S for reaction Z? Please determine that. Positive or negative, or is that the only option? Or zero? We are going from 2 moles of a gas to 1 mole solid and 1 mole gas. So change in S would be negative. I am getting more ordered, right? Or less disorder. So I went from 2 very high entropy states, of 2 moles of it I should say, to a very organized solid and 1 mole of gas. There is less disorder. And that's what you'd have to say if it says explains. So it would be a negative, and I would actually write 2 moles of gas, and now you went to 1 mole solid and 1 mole gas. And you might have one more follow-up little sentence saying it's gaining or it's losing disorder. or it's becoming more organized. You could say something to that effect. That's about as far as you can go. Awesome.
Would it be the same if like carbon was gas? Would it be?
It would be 0.
Okay.
Great question, though. Well, actually, no. If you had 2 moles of gas and then there was still 2, that gets tricky then. It depends on what it breaks up into, because it could be, well, you have 1 and 1, so it's 0. Well, it also depends on the molecules that are present. I mean, if there's more options for other things to occur, it could increase, but most likely then that would be a 0. They wouldn't have it in such a gray area. Usually it's very cut and dry.
Yeah, I like mathematically kind of did it because I flipped it, and then like you flip the S's. Can you do that, or is that just what you guys?
S's.
On the chart, if you like cancel flip and cancel out.
On like
Sure.
on reaction X and
Oh.
Y, like if you took like, because the COs both are on the product side.
Yeah, you could, but if you say, like you did the other day in class, I did it on my calculator, and that was actually what you wrote down, you will not get any points, because they won't know what you're talking about. Like, you would have to show all that.
All the work.
Yeah.
Alright.
Okay. Yeah. Here's my address and phone number. Call me about what I did. I'm available during these times. Thank you for your consideration. All right, that was I. Double I. Determine the value of change of H. What do you do? Rory actually just kind of pulled the curtain away on this one. What do you do?
Flip and change and flip and change.
So it's Hess's law. This is Hess's law. If you didn't notice, these were the other. What do both these have to do to equal this? So if I add these two up, x and y equals z. What? Sorry, you probably just said it. What do I have to do to both? I think both have to be flipped, don't they? And the reason why I just see that is I see the two COs and I need 2 COs here. Do I have to do anything with magnitude? I don't think so, because these would cancel, right? These would cancel, and there's my C, and there's my CO2, and there's my 2 COs. So they're both flipped, so magnitude is flipped. So I would just add them together. This is just Hess's law. Help me, tell me if I'm doing anything wrong here. Technically per mole, but if you just put the kilojoules, that's fine.
When do you multiply that? I remember.
If you would have had if you would have had to double one of them, then you have to multiply it.
What do you mean the double? Okay.
If you needed like 2 of them.
No,
then-
like multiply like to a change of H.
Instead of adding them.
Oh, that's not with that. That's K's,
What? Okay.
which I know is really confusing. Last one. A sealed glass reaction vessel contains only CO and a small amount of C. If a reaction occurs and the temperature is held constant at 298, will the pressure in the reaction vessel increase, decrease, or remain the same over time? So let's look at the equation. It's saying, let me reread it. A sealed reaction contains only CO and a small amount of C. If a reaction occurs and the temperature is held constant at 298, will the pressure in the reaction vessel increase, decrease, or remain the same? So that's all I have in the beginning. So talk to me about one thing that's going to happen, not the final answer here, but what's one thing that naturally has to occur on this reaction? Because this is all I have in the beginning. What's something that we know has to happen?
CO2.
Well, how do I know that? It doesn't say that. Does it say that?
It's 0. Each be equal.
Yeah, everything needs to be present in an equilibrium reaction, going both ways. So the reaction will naturally shift to the right, making more of this. Okay, so if I know that now, think about this for just a second. Pressure is based on the gases. So what's going to happen to my overall pressure? I don't need to know numbers. I just need to know in general. Christian, what's going to happen?
It's going to go down because it forms the solid part.
Okay, besides that, you're right. focus more on what the pressure is. Why is pressure going to go down? It's okay if you don't. I'm kind of changing your answer. So
Based on
it could be. Luke, what do you got? That's not. You're on the right track. So you're on that.
Because there's only 1 mole of the gas on the right and 2 moles of the gas on the left. So
Okay.
if it's going right, the moles would be decreasing.
So you're increasing 1 mole of gas and decreasing the 2 moles of gas. So in the overall, you're going to be creating less gas pressure, less gas. Right? You're going from, this is how I would word it. I'll read what they have. But it will shift to the right because the reaction will produce CO2. This will cause the reaction to produce less of the 2 moles of gas and be producing more of the 1 mole of gas. And the pressure decreases. Let me read what they have exactly. And sometimes what they write is more specific than needed, sometimes not. Reaction will proceed to the right, forming more C and CO2. Because 2 moles of CO would be consumed for every mole of CO2 that is produced, the total number of moles of gas in the flask would decrease. And you know what? It's a better way to say it. The total number of moles of gas will be decreasing. That's just a good phrase. Thereby causing the pressure in the flask to decrease. I hope it makes sense, like after you see it at least. I saw some of you when I first asked you, like, I don't know. So Rory started us off, and then we kind of finished it up, like, you got to make what's not there. You have to make what's not there. And because of that, you got to look. Pressure is always based on gas. So if there's less gas being made, there's less gas being made. There's less pressure. If there's more gas being produced, then there's more pressure. This is a really good problem as an overall like review idea because it kind of talks about everything. All right. Let's get to the electrochem and then we'll do like a 5-minute break or something. Sprint around the building. Electrochem. All right. So I put the picture up here. I thought it would be a good visual for us. They gave us a lot of imagery on here. By the way, one thing for you to notice this right away, please. Notice that both electrodes have PT on them. And we talked about this a long time ago, but it literally hasn't been addressed since October. PT is usually considered an inert electrode. It is there because it can help with current, because it is a metal, but it is not actually part of the reaction. It is just helping the reaction go through. So the reaction is actually through ions within the solution. You'll see that with solutions, and you'll see that with a gas. You could literally have H2 gas being pumped in, let's say, and then you'll see this weird device. And then inside will be a PT wire. The wire is just there to help with the current, but the hydrogen would be the actual one in the reaction. So if you're like, well, I don't get it. Well, they have the equation down here, and the PT is not there. So they're not trying to trick you. It's just, it's not actually involved. It's just helping with the flow of the electrons, or else the electrons would not be able to, you can't just have them flow into solutions. You need to have a metal, but a PT is unreactive.
For the test that, are they always going to have the, whatever metal gets reduced or whatever on the left, and then whatever one's gaining on the right?
9 times out of 10, that's right. But I'm sure this next Monday will be the time that it doesn't, because that's just the way it works. But usually they set you up and ask you things and everything else. Then they gave us a couple half reactions. So these are reduction potentials. Notice, please, before we move forward, is that the electrons are both on the same side. But if you take these right now, that would not mirror this equation because one has to flip. Right? One has to gain electrons, which is on the left side. One has to lose electrons, which would be on the right. So one of these has to flip, and that's part of this whole problem. All right. So a galvanic cell and the balance equation for the spontaneous cell reaction are shown above, which is over here. The 2 reduction half reactions for the overall reaction that occurs in the cell are shown in the table below. A. On the diagram, clearly label the cathode. Okay. So what you have to do is you have to figure out where this is flowing. So here's my actual reaction. I underline it in black. And this is the actual reaction. So more or less, the electrons have to flow from here to here. Okay? So which let's do this. It's not going to ask you which way are the electrons flowing, clockwise or counterclockwise. Just looking at the solutions here. Clockwise, like this. Is that what we're saying? And the reason why is that the equation shows it. I have Fe2 plus and MnO4 minus. Oh wait, oh no, wait, that doesn't make sense. MnO4 minus, that's over here. But here's the key part. The Fe2 plus, and then here is the Mn2 plus. Okay, we'll talk more about that in a minute. But that's the only one in there, and that's the only one in here. Just, we'll get there. I can prove it to you in some other way. So, which one is the cathode? Left or right? It always goes in alphabetical order of the flow. It goes from anode to cathode. So if the flow was going this way, it'd go from anode to cathode. So this is cathode. Okay?
How would, like, the Fe in the equation flip? Is the sheet that you gave us, like that white sheet, is that oxidized thing, or is that
Okay, so
you know what I'm talking about? Like the white sheet with all those numbers?
yep, that's what these are.
Yeah, is that
These are half reactions.
but is that like a reduction, or is that
These are all they're always reductions when they're given to you because reduction involves gain.
okay.
But one has to flip. One has to flip.
So then the one that doesn't flip is non-reduction, right?
It's oxidation.
Yeah.
Yeah. So I'm going to talk about that. We'll get there right now. So I'm actually going to prove letter A, if you don't get that, with letter B. It says, calculate the value of the standard potential. What's the goal with these? This is the standard potentials. So you can actually figure this out because if you look at this and you look at the equation, if you look at the two half reactions, you can see what happened. But let's say I wasn't given this. They actually bailed you up. They don't have to give this to you. They just give you these. What's the goal that's inside my circle about a cell? What do I want? I want the most positive value I can get, period. The most positive. One always has to flip. So if I flip the bottom one, I get negative 1.49. I add those together, I don't have a positive number, right? So I have to flip this one. So that one is flipped, and that's why now Fe2 plus is on the other side. So when I add all that up,
Don't you need to multiply that by 5 or no?
no. Voltages, it's confusing, but voltages never are affected by the magnitude. But very good. You do need that for the electron. So just want to talk about that for a second. This is why I know that this one, it's losing electrons. So the Fe2 plus is losing electrons. The Fe2 plus is losing the electrons. Even if you're like, yeah, but the Fe3 plus is in there. Why isn't it over here? It loses it and it becomes that. It's not like it can live in the other solution. It's not like, oh, the Fe, and then just, and then like the ion goes through it too. It's only the electron. Oh wait, but you have MnO4 plus on the other side too. Same idea. You start with MnO4 plus, and then it becomes Mn2 plus. That's the direction it's going. That's how I'm reading this. And it's within the same solution. So this is kind of a unique electrochem. It's not metal to solution, it's ion to ion. But it has to stay in the same cell. So what you got to just realize is how that direction goes. The only way this can happen is if it loses an electron. These are gaining electrons. This has to gain an electron to become that. Both those are worth 1 point. C. How many moles of electrons are transferred when 1 mole of MnO4 is consumed in the overall reaction? All right, this is 1 mole right here. So Rory, what's the answer? How many moles of electrons? 5. How did you know that? Because you look at this right here, and there's 5 here, and there's 1 mole of this. This has to react. You need to have 5 of this. You need to have the same number of electrons. That's the basis of all redox. You have to have the same flow of electrons. Layla. Like these? You never. I know, because it seems like it's like Hess's law. Voltages are just voltages. All we can do is manipulate signs. We can never manipulate the amount. Okay? And I know that is very confusing. All right, D. This one's a little shorter than the last two, which is okay. Calculate the value. Okay, so I gotta say this. You need something that's not on your equation sheet for this. It used to be. So if I gave you this, let me just read it first. Calculate the value of the equilibrium constant KEQ for the cell reaction at 25 degrees. Explain what the magnitude of K tells you about the extent of the reaction. Okay, in general, before we do that, the magnitude of K. The larger the K, what does it mean? Am I going to the right or left? To the right. So that means what? That the cell would go more to completion? That's what that would mean. Okay, if the K was more to the left, then the cell would not go nearly as far to completion, so it wouldn't be as ineffective of a battery. You would need to know this. Like, you would have to be given this. So let me just write this down for you. Just understand that this is not on your sheet, so this is probably not going to be asked this way anymore. But I do want to just show it to you. So this is a thing called Faraday's constant. Takes into account a lot of different things. So you plug these in. Let me just show you some of the numbers because I do think it's important. N. With N, there are equations that you do have. N for any electrochem problem is the number of moles of electrons. Okay, that's always what we're talking about. The energy is what we just did. And then we just put it over this. Again, you would not know this. But maybe they told you this part. So I do want to stay true to the question. That's a big number. So what I just said, what does the K tell you? The K tells you that this cell, or this reaction, is going to go basically to completion, right? It's going to completely drive all of the electrons from the left, from the anode to the cathode, because it's a huge K.
Where did you get the 6.5?
That's the answer. I took second in log of 61.
Oh, okay. Okay. Could you just write that 10 to the 61st?
No.
Oh, wait.
This is 6.5 times 10 to the 60.
Okay.
So, it's a little out of context because that equation is not exactly expected any longer. But understanding this is. So let me read it exactly. Because the magnitude of KEQ is very large, the extent of the cell reaction is also very large, and the reaction goes essentially to completion. And I just realized that I didn't get to finish, and it's really important. So on Tuesday, we need to go over quickly those last three little problems of the last electrochem that we did, because it was like, this thing happened to your cell. What occurs? It's really important to understand what happens to voltages when something is altered in a cell. So we do need to talk about that.
In C, how would the answer change if it wasn't 1 mole of MnO4 minus?
Yeah, it would have to be reflected. So for example, if there was 2, then you need 10. Because for every, according to this, for every one of these, you'd have 5. So if somehow this was, if there were 2 of these, then this would double, or whatever. But you need the same amount total, so, yeah. I've never actually seen them word it like that. Usually they just say how many moles of electrons are present, and then you just look and you match them up. It's not 6, though. So we just went back on one, but like, just to bring that up, and he said, like, you don't add them. They have to be equal. Okay. Finishing up the last 2. E. So they reset it. 3 solutions. This is going to be a little confusing. Hopefully it'll make sense. 3 solutions, one containing Fe2+, one containing MnO4, and one containing H+. By the way, those 3 things are your reactants. Are mixed in a beaker and allowed to react. The initial concentrations of the species in the mixture are 0.6, 0.1, and 1.0. E. When the reaction mixture has come to equilibrium, which species has a higher concentration, Mn2+ or MnO4-? Let's look at what they're asking. They're asking which one is there going to be more of. So basically, they're just saying, is this going to drive it over there, or is it going to stay with MnO+? And you have to kind of explain Why? So, one reason. What's one reason that we know that's going to be more of one or the other? Based on just everything we've just done. Decay. Good. Don't we know that this is basically essentially going to completion? So right away, the first thing I can say is that definitely the concentration of Mg2, not Mg, Mn, will be greater than the concentration of MnO minus, O4 minus, goes to completion based on K. And that's great. Unfortunately, sometimes there's like hidden answers, and like that's worth one of the two. If you commented on that at all. Okay. The other one, you have to somewhat talk about the idea. Let me write this down. For every one of these, I need 5 of those. Right? For every one of MnO4, I need 5 of those. So if I had 0.1, what would I actually need to react perfectly? I would need 0.5 of those, right? And for every 8 of these, so I would need 0.8 of H plus to react perfectly, right? So what does that mean? When I would only need, I only need 0.8 and 0.5. So the other answer, somehow, you'd have to say is that that's the limiting reactant, or it completely goes because you have excess H plus and Fe2 plus. And I don't know if everybody would get both answers, but I'm just telling you what the answer he says. You have to refer to something that you have excess H plus and Fe2 plus. Consuming the Mn O4 minus. Something to that effect. If you're like, oh, I wouldn't have said that, but I hope at least it makes sense. To be honest, I don't know if I would have said it. Because I think I would have been so hooked on the idea of the completion, be like, well, it's going to drive it to the right, so there's going to be more Mn2 plus than MnO4 minus. So anyway, just for you to know. All right, last one, and then we'll take a small little break, and then we'll finish up, and we will end on time. That's my goal. When the reaction mixtures come to equilibrium, what are the molar concentrations of Fe2 plus and Fe3 plus? Let's talk about that. And I'm writing it literally like this. Like I'm thinking like this is a reactant, that's a product. I think I got that right. Yes. So how do I figure that out? Well, it's based on the entire equation though. So what's happening with Fe2 plus? Consumption, right? So it's based off of the limiting reactant. Let's talk about how that would look. It looks like this. I'm doing the form of an icebox right now. I have 0.1 and 0.6. So how much is going to get consumed? What did I just say before? It's a mole ratio. So I mean, if you're thinking about this, it'd be 5 over 1, right? So what I need is 5 molar, right, to consume. That, right? So what would be remaining is 0.1. Okay, what's being produced? Well, I'm starting at 0. If you look at the ratio, there's 5 in front of here. There's 5 in front of here. Just write it like that. So how much do you think is made? 0.5. Wait, what? Well, if I'm using up 0.1, you can do from here or from here. If I'm consuming 0.1 and that's 1 mole, it would make 5 times that. Or, hey, 5 moles of something, that's how much was consumed, and that 5 moles of that would be the same answer. So, it's going to be 0.5 molar produced. 1 point is earned for the correct setup, including the correct setup for an equilibrium calculation. So I'm doing it more as an icebox, or you could do actual like ratios, like ratio works. And then 1 point is earned for the correct numerical answers. I hope that the way I did it, maybe I shortcutted it a little, but just trying to show you how that could be. So, all right. So if you want to just take a walk for a second, we'll start in about 5 minutes, 10 after 10, so 4 minutes.
Is there like any like a
All right.
I don't know. I've never.
So, a rigid 5-liter container contains 24.5 grams of nitrogen and 28 grams of oxygen. A, calculate the total pressure in ATMs of the gas mixture in the cylinder. There's a couple ways you could do this, but when it's all said and done, you need pressure. You need total pressure. So, what do you think you have to do with that? You need moles. If you get moles of those, you have V here, and you have T here. You need pressure. P equals nRT over P. You have all the other ones that you need. Okay, so you can do this 2 times. You can do 2 different pressures, or you can do the moles combined. What do I mean by that? You can do the total pressure 1 time, or you could do 2 of these. I'd rather do an equation once. So this is how I would approach this. We need moles. Show your work. So again, what am I talking about? You could plug in nRT over P and nRT over P, or you could do N total RT over P and do it once.
Why are you putting P on the bottom?
I don't know. Doing it wrong, Kyler. Thank you. So, know that you can do either one. But if you do these bottom 2, what do you have to do then? Still have to add up the pressures anyway. So it's the same amount of work. But if that's the way that it kind of clicks in your head, you're like, well, yeah, I got to find the pressures of each, and then I add them up. Great. It's Dalton's law of partial pressure, and I'm combining them all. But I could do this all. So let's actually see if I know what I'm doing here. Bless you. So that's how it could look.
What's the unit for the rate constant?
The rate constant, it will be on your yellow sheet, but it will be, they have it written oddly, but it'll be ATM, liter, and then what I do it underneath, but what they'll have then is this. That's how they'll have it written. So it's ATM liters over moles Kelvin.
Should we?
And on the actual test, I strongly suggest writing the unit. Just, oh gosh, it's so much. It's right there. Just copy it. Just copy it. My suggestion. So when I'm all said and done, please put units. Please put units. You always get 2 points just about every time you do an ideal gas law. 1 point is earned for the setup. In this case, 1 point is earned for the moles, and then 1 point is earned for the correct answer with the setup. So you did have to have the setup all put in there. So that's just letter A. Or, yeah, letter A. B. The temperature of the gas mixture in the cylinder is decreased to 280, so it's going down. Calculate each of the following. I. Mole fraction of N2 in the cylinder. What? Okay, if you don't if that's not clicking, or what's a mole fraction? It's the moles of that one thing over all the moles. Just like any fraction, it's the percentage, it's the part over the whole. So, well, you would just simply put it's the part over the whole. So if you already knew that number, you could put the whole thing in right away. But that's just 0.5, isn't it? Right? There's no unit. There's no unit on that. It's just 0.5. And I'm being sloppy. It should be 0.500. A good role model here for you. 1 point. By the way, if for some reason you messed that up and you did pressure over the partial pressure over the total, like you did the pressure for nitrogen and then you did it over the total, somehow you had that, you could have gotten a point for that too, because it would have been 50% still. Double I. The partial pressure and ATM of N2 in the cylinder. Okay, so there's a lot of ways you could have done this. A lot of ways. And I want to show you just quickly a couple of them. So you could have done the overall, you have to redo the pressure, so the pressure at 280, and you could just do the total, so you do all of it, or you just do up nitrogen, I should say. Sorry. So you could do the nitrogen times, and then it's 280. R values. Could have gotten it that way. Okay. Or, I wouldn't have thought of this. That's how I would have done it. You have a before and an after. And what do I mean by that? You have Gay-Lussac's law, P over T. Meaning you had 8.56 ATM at 298. And now it's asking for, this is the easiest one. I would not have thought about this first. You could have done that. It almost seems a little bizarre. It's like, oh my gosh, I could just do one of those gas laws? Like, when's the last time I've done one of those gas laws? You have a relationship there, though. That says P over T, or PV over T. So, you could have done that. Yes, you learned that as machine about this.
Would you have to multiply P2 by the mole fraction?
Yeah, right. Sorry, yes. So then this would be, good job. So this would be the total. Nice, Dane. And then you have to take half of it. Good. Because this is the total volume of both. This is of oxygen and nitrogen.
What if you do the top way?
Top way is fine because I only did of nitrogen. Yeah. But, I mean, this is probably about the same amount of work, you know. Either way, you get 4.0 ATM. 1 point. That's it. You only get one. I would have thought you could have gotten a little bit more out of that. But you only get one. C. If the cylinder develops okay, we just had a quiz on this in general chem yesterday. If the cylinder develops a pin-sized hole leak and some of the gaseous mixture escapes, would the ratio of this, it has to be this exact ratio, in the cylinder increase, decrease, or remain the same? So it's a mathematical question. So first let's talk about this. Which one will effuse faster? Anybody remember what effuses faster? Rory.
N2.
Why?
Because it's lighter.
Lighter, less mass effuses faster. So this will effuse faster, the N2 than the O2. So the overall ratio, the questions about this whole thing. So I would say N2 would effuse faster because it is lighter. So the ratio will decrease, right? That's it. You don't need to start explaining, because the number on the top will then be smaller than it decreases. And that's when you're going to mess up where the numerator and the denominator are or something. What's on top? A stalagmite or stalactite? You should never get that mistake. It's stalactite because it's hanging on tight.
Take some mice.
All right, a different rigid 5-liter cylinder contains 0.176 moles of NO at 298. A 0.176 mole sample of O2 is added to the cylinder where reaction occurs to produce NO2. Write the balanced chemical equation. My goodness, they gave you everything. Can you write this equation? They've told you what was added and then what was made. Figure it out. Try to figure that out once. You might have to balance it. It says write the balanced chemical equation. So I have NO, O2 is added, and it produces NO2. And then you need to write a balanced equation. I hope we have that. If not, please reread it and go like, oh yes, there it is. And then finally, last problem. That's 1 point, by the way. Calculate the total pressure in ATM in the cylinder at 298 after the reaction is completed. What? Okay. If it talks about total pressures or concentrations and things like that, you have to do stoichiometry. An easy way to do stoichiometry is an icebox. They made you do an equation on purpose. So I'm going to actually just put it right under here. So I did it differently than the answer key because this is kind of the way we more learn. I have this. And it's moles. We'll talk about that in a second. You can do moles, you can do molarity, you can do pressure in an icebox. You just can't do grams. I added 0.176 moles of this. So I have 0 right now of that. So it has to drive it to the right. And I don't think it says how much was made, and that's part of the point. So I hope this makes sense so far. So what I'd like you to do right now is, what are those bottom numbers? What are my E's? Can you figure that out? What is that? You're like, well, I don't know what I'm going for here. Well, something has to run out. Think about it. So, I want to know what's E? Give you a second. You have 40 seconds to try to figure that out. You have equal amounts, but you don't have equal moles, mole ratios, I should say. Who runs out first, NO or O2, if you have equal amounts? NO. I need twice the amount of that. So if I have this, for it to react perfectly, I need double that, and I don't. So X is not 0.176. This will be 0. This is the limiting reactant. And when I finish it, hopefully this will make sense. The X is 0.088. It's half of that amount. Because when this is all gone, only half of that is gone. Now, this is not an equilibrium problem, so it's not about if it now has to drive back this way or whatever else. Now it's just asking for the total pressure. It says calculate the total pressure when I'm all done. So what am I doing then? What do you think? PV equals nRT, and these are my 2 moles. We have one's on the right, one's on the left. They're in the container all together. This was in the container in the beginning, and then it produced some of that. So, finishing it up. I hope that icebox makes sense, the way I did it. The way they did it was a little more confusing. I tried to put it more in terms of maybe something that would kind of click. my final pressure. All right. A little bit shorter one, and then we'll see how many equations we get in. We're fitting this nicely. All right, this is more about just IMFs and bonds and things like that. So, structures of pyridine molecule and the benzene molecule are shown below. Pyridine is soluble in water, whereas benzene is not. Keep that stuff straight, too. As you're reading in a problem, if you're ever confused, you might want to just make sure that you're understanding which ones are being spoken on. Account for the differences in solubility. You must discuss both of the substances in your answers. So you can't just say why one is soluble and one isn't. There are good ways to do this. You can talk about the similarities and then the differences, or you can talk about why one is soluble and then why the other one isn't. You have different choices, different situations kind of provide that, depending on what you need to speak on. So this is actually worth 2 points. Yes, the 2 points kind of go off of the structure and then why they're actually soluble or insoluble in water. So let's talk about water for a second, just so you have an idea. Water looks like this, right? And I break it all down and have all my knowledge. Water is very polar, right? It has high attractive forces. It has H bonding, and that is why things dissolve. To dissolve, like dissolves like. To dissolve in water, you have to have attractive forces to the water, the H bonding specifically, those sites. So like an H has to bond to the O, or the O has to bond to an H, and you have to, or another atom that is going to create a dipole or an attractive force. So first, what I would say, you could say a lot of things, but this is polar, right? This is polar. This is non-polar. Right. This has an asymmetrical structure. I'm trying not to read what they're having because they go really, really specific on one thing only. That causes there to be partial charges. Okay. So this is polar. This is asymmetrical. Okay. This also with water. What can be created? Why can this dissolve? It can create a H bond, which is an IMF. It's not an actual bond. So you can have H bonding with water. While this one, there is no attractive forces. There will be no interaction. There will be no interaction. There's only LDs. So there's no attractive. It's kind of a cumbersome problem. I'm going to read what they actually have. I was trying not to read it all. I didn't want to put anything in there that they specifically had. Pyridine is polar and capable of forming hydrogen bonds with water, while the nonpolar benzene is not capable of forming hydrogen bonds. Pyridine will dissolve in water because of the strong hydrogen bonds or dipole-dipole intermolecular interactions that exist between the lone pair of the electrons on the pyridine nitrogen atom and the solvent water molecules. No such strong intermolecular interaction can exist between benzene and water, so benzene is insoluble in water. It's very cumbersome, but you kind of get the idea. Again, this is nonpolar, it's asymmetrical, there's no charges, it's only LDs. This is polar, it's asymmetrical, it has partial charges, but more importantly with the water, you can have H bonding with H2O while this has no attractive interaction. Okay, so sometimes they are a little more cumbersome and they're not as neat and tidy. Let's see if this one is any less. These are the two longest of the four on here. Structures of the dimethyl ether molecule and the ethanol molecule are shown below. The normal boiling points of dimethyl ether at 250 degrees, of dimethyl ether is 250 degrees, or 50 Kelvin, wow. Whereas the normal boiling point of ethanol is 351. Account for the difference in boiling points. You must discuss both substances in structure. So identify what they have. This is how I would say it. Identify what they have and then explain why it's a higher or lower boiling point. So if I want a higher BP, what corresponds to that? So things are attracted to each other. Kyle?
Stronger bonds.
Stronger bonds, more specifically stronger IMFs. It's not the bonds. I'm not breaking these apart. Okay, I'm breaking one compound from another. Right? It's still like boiling water is still H2O when it's a gas or when it's a liquid. So you're breaking it apart from one attractive force to the other. So you need to talk about each of these first. So what could you say? This is the lower one, so it should have lower IMFs, 250. This has 351, this should have higher IMFs. So what kind of IMFs does dimethyl ether have? Where? That? Problem is there's this one. They're all canceled out. If dipoles cancel out, they don't exist. If they can't, CO2, great example. Oh, a dipole. Oh, dipole. Oh, shoot. Non-polar. They cancel out. So these are London. What's this one? Definitely an H bond. So first, you should explain it. This one is non-polar. All dipoles cancel out, so only London would exist. Whereas ethanol has hydrogen bonding due to the H-OH bond. Then, so now I've talked about the structure, and now I can explain why one has a higher boiling point than the other, or I can just say then London forces are weaker IMFs, causing it to boil much quicker or not being as attracted to other molecules, versus the ethanol where the H bonding will require more energy to boil because it's a stronger IMF. Or you have to refer to something about the strengths. You have to identify that H bonding is stronger than LD. Your job is not to explain what H bonding is. You have to say, well, H bonding is like a super dipole because the electronegativity differences are greater than a normal dipole because it falls into a range. You don't have to do all that. And I know that because I've asked multiple scorers. I'm like, do we have to have them explain what H bonding is? And they're always like, no. You have to identify that it has H bonding. You have to say that it's stronger or weaker than something else. Long explanation, but we've kind of said it here. The intermolecular forces of attraction among molecules of dimethyl ether consists of London forces and very weak dipole-dipole. In addition to London forces, and dipole-dipole interactions are comparable to strength to those dimethyl ether. Ethanol, sorry, I think I skipped a line. Start over here. Ethanol can form hydrogen bonds between H of one molecule and the O of a nearby ethanol molecule. Hydrogen bonds are particularly strong intermolecular forces, so they require more energy to overcome during the boiling process. As a result, a higher temperature is needed to boil ethanol and is needed to boil dimethyl. Great, finishing it up. The other ones are a little shorter. SO2 melts at 201, while SiO2 melts at a crazy number. Count for the differences. So melting points. So please understand that's from a liquid to a solid. I mean, solid to a liquid. Make it. So clearly, which one has a stronger IMF? SO2 or SiO2? By a lot. So maybe you don't know what this is. SO2 is tough. And I don't know if they'd address this, but yeah. No, this one. It's not CO2. It looks like this, just so you know. That's actually what SO2 looks like. It's not like CO2. And the reason why is that it's two further away, so it has two less electrons. It needs to share more. I mean less. It needs to share less, so it doesn't have to have the double bond. Dan, I heard you say it. What does SO2 have? What's the grade called? You need to know the phrase to the extent of just saying they are strong covalent bonds, like anything like that. They are really strongly bonded together. These, the best we have, dipole. It's a dipole-dipole. It takes a lot more energy to overcome the forces to cause it to go from a liquid to a solid to a liquid in a network solid than it does in a compound that just has pretty weak dipole-dipoles, by the way. They're right next to each other. There's not even a big electronegativity difference.
What are the network solids?
Network solids are anything with like if you see silicone come up, and see, they go other way. They're not expecting you to just come out of that from scratch. If it's this huge number, you'd be like, oh, silicone and carbons. But it's not just any carbon. It's not like CO2. It's one that can repeat. So usually like graphite, a diamond, and then like this is called quartz. These are basically the ones you need to know. But they'll usually give you an extra clue. So if it's just some crazy number, network solid. Okay? Again, those are really strong covalent bonds that are formed. And it's all networked. I mean, it's not just one bond. It's multiple bonds. There's a lot of strength in that. Okay? So that's where we're coming on that one. And I'm just trying to identify some of them for you. And then lastly, D. The normal, this one's good. I like this question. The normal boiling point of Cl2 is 238, while HCl is 188. It's underlining. It says it's higher. They're basically saying like, what? Because what's going on here? Cl2 has what? These are just London. This would be so if I didn't tell you which one is which, what would you have to say? Like you don't know. Let's just say I said X has 238 and Y has 188 Kelvin. What would you say about this boiling, this IMF versus that one? It's stronger. So now I show you that and I say these are here. What do you still have to say then? The LDs of Cl2 must be a stronger IMF than the dipole-dipole. Here's the reason. Why are LDs stronger? They're bigger. What's bigger? What's the actual thing that's larger? From one LD to the next. If I have a stronger LD, we always say, oh, it's the larger thing. What's the actual thing we always say? It's the larger, and that's not the atom. The atom is the size because of the electron cloud. The electrons come and then affect other electrons and then they move. That's actually how LDs are made. If you look at this, how many electrons does ClCl have? 17 each, or 14 valence. HCl has less electrons. Now, you may not, I'll have to check the scoring. You may not have to get to that point, but you would have to deduce basically saying that the Cl2LD force must be stronger than what appears to be a weak dipole-dipole. Layla? Yeah, that could come up a little bit, definitely when you do boil something. The heavier, well, yeah, the heavier it is, the greater the boiling point. You could bring that up too, but the main thing of this would be still the dipole. Note, it's not like you had to memorize that. It's not like, oh my gosh, I have to memorize it. No, they present situations. Then can you explain them? So, is that kind of a trick question? I think so, but at the same time, we could definitely handle it. So that's actually the reasoning behind it. I'll read it once. The intermolecular forces in liquid Cl2 are London, whereas the intermolecular forces in liquid HCl consists of London and dipole-dipole. Everything has London, but this says dipole-dipole. Since the boiling point of Cl2 is higher than the boiling point of HCl, the London forces among Cl2 molecules must be greater than the dipole-dipole forces in HCl molecules. The greater strength of the London forces between Cl2 molecules occurs because Cl2 has more electrons than HCl, and the strength of the London interaction is proportional to the total number of electrons. Last one, and we are done. So we'll do this pretty quickly. I like these. It's not the same format anymore, but I think it's really important. So stay with me here, and then we are done. Solid copper 2 sulfate pentahydrate is gently heated. Okay, copper 2 sulfate pentahydrate. How do I do that? You put a dot, and then what am I writing? 5H2O. Is gently heated. Gently heated. You did this last year in the lab with a crucible, and you heated it really lightly. In terms of heating, you did it lightly. They're saying that on purpose. What do you think's coming off of here then? They're basically just severing off the water. That's what they're doing. When something's gently heated on a hydrate, There's nothing else that can be done. You are trying to basically strip off the water. That's it. That's the equation. But I do want you to see this part. How many grams of water are present in 1 mole of copper 2 sulfate pentahydrate? Okay, so I have 1 mole. Kind of start to the side here because it's going to take up some space with radius. I want to know water. So this is what you have to do, guys. I'm starting with this whole thing. I have to get just the water. So I have to do a ratio between them. So what's the ratio? If I do moles of water, because I'm trying to get the water. I want grams of water, so I got to get into moles of water first. Reminder, if you ever start with something and it's asking about something else, you have to go through moles. So this is just like stoichiometry. I mean, you could literally go from here to here. You can envision it that way. So I start with moles of moles of this. I want to find grams of that. So I start with moles. I do mole ratio. So there's 5 moles of this for every 1 mole of that. I mean, that should make sense just on the balanced equation. There's 5 of these for every 1 of these. And then now I'm in moles of water. I can finish it off. That's just stoic. Just the flow chart, right? Grams, moles, 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 grams. Here I just started at moles. So it's like 90. All right. 2 more. 2 more, 2 minutes. Excess concentrated aqueous ammonia is added to a solution of nickel 2 nitrate, leading to the formation of a complex ion. Yes. All right. So, and technically these are supposed to be net ionic. We'll talk about that in a second. So, I'm sorry. Okay. So concentrated ammonia is added to a solution of nickel 2 nitrate. So nitrates are very soluble, so it should look like this. Making a complex ion. So what has to happen? The ammonia is going to come in. It's going to break that apart. And it told you it's going to make a complex ion. So you always put the transition metal first, and then we're going to add a ligand. How many? 4. What's my charge? NH3 is neutral. There's no charge on it, so it's still a 2+. And my final question always is, do I feel good about having a 2+? Only if I have a negative that would be there. What would be my negative partner? My NO3, but it would come out a solution. Nitrates never do. So it would be like I'm writing it here, and I'm like, oh, it's gone. So then I just need to balance it. So there's my equation. And this thing just keeps haunting me. A Lewis acid does not have lone pairs on it. A Lewis base has lone pairs on it. That's it. Instead of giving and taking H's, what they do is they give and take electrons. So between these two, it's the reactants. Which one does not have electrons? Why do I know that doesn't have electrons? It's a positive charge. It gave away everything it had. Well, yeah, it has other ones, not valence electrons. Well, how do I know about NH3? Electrons. So the answer is Ni2+. Why? No electrons. Okay. I know we're already 1 minute over, but at this point, let's finish it up. We all leave. We have like one last little part. I'm out. Methylamine C3NH2 is added to a solution of hydrochloric acid. And that's all that says. There are multiple ways to do this one. When I react hydrochloric acid, what's the main thing that matters of hydrochloric acid? Yep, so the one that matters is the H plus. Right? So, wait a minute. I'm adding HCl. It doesn't say this, but what do you think methylamine is then? If I'm adding an acid, methylamine must be a base. Wait a minute. That's the equation. Methylamine dissolves in water to form a solution. Indicate whether this solution is acidic, basic, or neutral. Okay, so unfortunately you actually have to think about another equation. But this is what I think of, and maybe you could have already gotten to it. You wouldn't need to draw it out, but if it reacts with water, it's a base. I'm adding it, this is a classic basic equation that we've been having. It did not ask for the equation, but what's the answer? Basic because, and it says justify because, you always have to say, because Brody said, because OH minus is present, or was produced, right? All right. And hopefully we'll see you tomorrow, 1 to 5, in LGI 1. Appreciate you stopping by.